2D Dige. Okay, what does this stand for? This stands for two-dimensional differential gel electrophoresis. All right, so 2D differential gel electrophoresis. Now your sample preparation for 2D differential gel electrophoresis is pretty straightforward in that you have two different specimens. And so I think the easiest example that I can come up with this, or maybe the most straightforward example, would be, let's say you have someone with bladder cancer. You have a person who has bladder cancer and a person who does not have bladder cancer. And let's say hypothetically that you wanted to evaluate these two people's liver cells to see something, to see, what the impact of their bladder cancer has on their liver cells. And so for one of these two samples, you would add this Psi3 dye. This is what's known as a Psi3 labeled sample. Then for the other sample, you would label with a Psi5 dye. Okay. Now what you would do with these two samples is you would combine them ultimately and run them on a gel. And you would produce a Psi3 image and a Psi5 image. The Psi3 dye is you're only going to be able to detect proteins with light of a particular wavelength. Psi5, you're only going to be able to detect with light of a different wavelength. So think about it like if you shoot a wavelength of 490 nanometers, that will detect the Psi3, but not Psi5. Then if you shoot light with a wavelength of 650 nanometers, that will detect the Psi5, but not the Psi3. So turn one wavelength on, you see one image. Turn a different wavelength on, you see a different image. Then what you can do is overlay these two things. And this representation down here has a pretty nice comparison. If you look at these samples, you'd be able to see that, well, there's this one, 3, 4, 5. We've got 5 little proteins there. Then this one, we've got basically the exact same proteins, and you'd be able to see what makes them different when you overlay them. Now, imagine that this red one, the Psi3 image, the protein is shifted over a little bit or something like that. That's basically what you're supposed to see. So all of the proteins that are the exact same in terms of their positioning, that would be this one, this one, this one, this one, this one. This one, however, has shifted a little bit, so it's worth noting. Then say, oh, well, as it turns out, the Psi3 image, that's what I'm seeing, that's the protein that I'm seeing. So that protein in particular has changed due to the bladder cancer, whatever affliction that or whatever treatment the first specimen was given. Okay, so you're looking at two different samples on one gel, and you're able to do that because these dyes will be activated by different wavelengths of light. Okay, so what do figures for this actually look like? This is what one of these figures looks like. Okay, now what's worth noting about these is, well, when we compare the two different dyes, that's our differential. What we haven't talked about is the 2D part of our name. Okay, and that 2D, that two-dimensional, well, is right here and right here. If we look specifically at figure A, we've got a pH range from 4 to 7. And then if we look at our y-axis, we've got a pH, or we've got a molecular weight range from 130 to 25 kilodaltons. So what we have is first dimension is that you separate proteins by their pI using a technique known as isoelectric focusing. So in isoelectric focusing, a protein is going to migrate until it hits its pI. A protein that hits its pI is least soluble and has an overall charge of 0. So you separate by isoelectric focusing. You get all these proteins to separate and kind of position themselves based on their charge or based on their pI. And then your second dimension is you take that IEF strip, and it looks almost like a piece of pH paper. You take that strip and you lay that down on top of the gel, and the proteins, whenever you apply an electric field, here's my strip, here's all my proteins that have separated by their pI, what they do is they actually begin to migrate. So they leave that strip and enter this gel, in which case we're using SDS page, so they will separate based on their molecular weight. Now this is an extremely powerful technique because what you're able to do is do these huge evaluations. You're not looking at one or two proteins. Instead, you're looking at basically an entire proteome. And you can use pieces of software that analyze these Psi3 and Psi5 signals, overlay them, and they say, oh, well, when we compare this image right here, which I'm going to go with label A and label B, when we compare A and B, we get C. And I mean, heck, those look like a Jackson Pollock painting to me, and I'm not an art person. I can't make too much of that. But then, whenever I use a piece of software to tell me something, it can detect those subtle differences and say, oh, well, this protein right here and this protein right here, they've changed. What about them has changed? Maybe the molecular weight has changed. Maybe the pI has changed. So then you can say, okay, if the molecular weight changed, then you ask the question, how much? And thinking about this, maybe what happened is the protein went from 76 kilodaltons, or 76 kilodaltons, down to 72 kilodaltons. Okay, so that's 4 kilodaltons. That's approximately a 4 kDa difference. That is 4,000 daltons. So that's almost, I'm going to use a tilde, almost 40 amino acids. What happened to those 40 amino acids? Why are they gone? Well, maybe what's happening is there's a protease in one specimen that's very active, and it's going to cleave these chunks off. It's going to cut those 40 amino acids off, and they're gone. We don't know. That's the important part about this technique. It gives you a question to ask, and then all of a sudden you have this new avenue of research, and you have this new approach where you can say, oh, well, I've compared these two different cell types, or I've compared the wild type tissue and the cancer afflicted or whatever treatment tissue, and I can say, oh, well, this thing is different. I'm going to pursue that protein, find out what happened to those 40 amino acids. Maybe, just maybe, that could be avenue to begin research on a treatment for whatever this disease is, or whatever the treatment cost. All right, I hope that was helpful. Have a good one.